All right, so looking at page 92, we're talking about power series. At the top, we have frequently used Maclaurin series, so keep this in mind. You can just hang on to this. You can see on the right we have a indication of all the domains, all right, and where each of these exist. All right, so you could see what we had talked about, or what we had talked about for exponential e, sine, and cosine. That's the case of the infinite. All right, so that's going to lead us into the concept of a power series. So a little blurb here. If x is a variable, then an infinite series of the form coefficient binomial to a power, much like you would see for a Taylor series, and that expansion is known as a power series. All right, where c is a constant, but that c is what it's centered at. C for center, C for constant. Radius of convergence is going to give us a determination of under what the interval is, or under what circumstances this series converges. But if we're using it to model another function, something like a natural log or an exponential function or something like that, then it's giving us a sense of under what circumstances the series models the function. All right, so when it says find the interval, center, and radius of convergence, be sure to check the endpoints. That doesn't have a heck of a lot of meaning right now, but when I say that what that's telling us to do is find whether or not this converges and under what circumstances it converges, that gives it a little bit more meaning. All right, so we'll start off with first trying to get an idea of what method makes the most sense here. This looks an awful lot like something that would be related to a ratio test. All right. And it's really just this n here that kind of throws everything off. Otherwise, I would go with the root test. If I could take the nth root, if the top and bottom were nth rootable, then I would go that route. But it looks more like I'd have to go the ratio test. But I could be wrong. We'll see. All right. So if I call this a sub n, then a sub n plus 1 is going to be x to the n plus 1 over n plus 1 times 2 to the n plus 1. Well, we've seen this a few times already. We would call this x to the nth times x. Top, anyway. On the bottom, n plus 1 times 2. Well, I'll say, I was going to say times 2 to the nth. I'll just do it the way I've been doing it. 2 to the nth times 2. All right. So we're going to find the limit as n approaches infinity of the absolute value of this. I might have missed that open paren. We'll see. No, I got it. Over x to the nth over n times 2 to the nth. So x to the nth cancel, 2 to the nth cancel. But that's really all that cancels. However, the x can be pulled out of the whole thing because it's irrelevant to the limit. Now this whole thing by the ratio test should be less than 1 if it's going to converge. So I'm going to pull out the x. I'm going to write this as the limit as n approaches infinity. Now all that remains, a lot remains, but on the top, it's just going to be a 1. On the bottom, we have a little bit more. We have the 2, we have the, keep, change, flip, the 1 over n on the bottom, because it's really a 1 here, is going to get multiplied by, well, actually, I'm going to correct myself here. This is keep, change, flip, the 1 over n becomes n over 1, so the top is going to become n, and the bottom is going to become 2 times the n plus 1, which is 2n plus 2. Now we could rewrite this as the limit x times the absolute value of the limit as n approaches infinity of n over 2n plus 2 Now, the whole thing has to be less than 1, right? But it's an absolute value, so we'll have to keep that in mind. But at least I can tackle this little piece. It's not a marker. This little piece here is just going to amount to a 1/2. So I have x times the absolute value of 1/2. Now, I'm going to bring that x back into the absolute just so I can make it easier to take the next step conceptually. So we'll call that x over 2 is less than 1. All right. So I'm going to write this now as -1 is less than x over 2, which is less than 1. All right. So I want to call that the definition of an absolute value. It's not quite as simple as that, but that's one of the properties or relationships that comes from solving absolute value inequalities. So I'm going to multiply everything by 2 and get bounds of -2 to 2. That's an x. That's an x. All right, so these are my bounds. So the one thing that, it's kind of a quirk in the whole process is, it kind of lends itself to whether or not, maybe that's not the best way to say it, but you start thinking about the algebra versus the concept, or at least the techniques associated with sequences and series and how it all kind of blends together. And those endpoints of -2 to 2, you think it'd actually be pretty cut and dry that those, it says less than. It says -2 is less than x, which is less than 2. So -2 and 2 would not be included. But what we do have to do is test those endpoints, because sometimes, as it turns out, sometimes they do actually work as points of convergence. All right. So what we do is we test x equals -2, and then in a separate step we test x equals a +2. All right, so if I plug in a 2, and honestly, I mean, the problems that you'll see, they're kind of, oh boy, dad joke of the day, tailor-made to fit the circumstances, and so you'll see a lot of instances where things kind of clean up very nicely, and when that happens, you say, oh well, it's really not that bad. But in the real world, I mean, honestly, it's like, if you can start immediately seeing real world applications of this stuff, then you're ahead of the game. All right. Right now, it just seems very academic, but there are many real world applications that it's just it doesn't always seem apparent. But regardless, what I'm going to do is I'm going to go back to my original series, and I'm going to replace the x with a -2 and then with a +2. So the sum from n equals 1 to infinity, instead of x to the nth, it's -2 to the nth. And again, it's n times 2 to the nth. All right, so then I'd have to really, honestly, if you think about the beginning part of this unit, you can kind of look at this as like 2 additional questions, like a part B, a part C, where it's like, wait, there's even more I have to do? This is terrible / awesome, depending on your perspective. All right, so I'll start with the easy case.
I'm not sure.
Oh, excuse me. That was Alexa misinterpreting what I was saying. So we have the sum from n equals 1 to infinity of 1 over n. All right, so that's n to the first power. So what we would have to do is go back and investigate our p series. So this is blank by the p series test. It's just a question of whether it converges or diverges. But before we get there, let's take a look at the other one. All right, so I have negative 2 to the nth power. So negative 2 to the nth could also be thought of as negative 1 to the nth times 2 to the nth over n times 2 to the nth. All right, so, well, I guess I don't need the parentheses for the bottom part. I haven't had parentheses the whole way through, so there we go. So these would cancel, and I would be left with an alternating series situation. All right, now, for an alternating series, we had some conditions that came into play. So I'm going to take you on a trip down memory lane in a second. And we're going to see whether each of these converge or both or neither. So a quick refresher on the p-series test. If the p-value, so first off, it's got to be in the form of 1 over n to the p power. So 1 over n to the second, 1 over n to the first, 1 over n to the 1/2, whatever, it doesn't make a difference. If the p-value is between 0 and 1, inclusive of the 1, the series diverges. If it's greater than 1, then it converges. If it's less than or equal to 0, then it's not a p-series, it's some other type of series. All right. So that's the p-series. The alternating series has the two conditions. Has to be a decreasing series, excluding the negative 1 to the nth power, or n plus 1 power. And the limit of that a sub n has to be equal to 0. All right. So using that information, we're going to come back to our example. Hopefully I'm on the right page. There we are. And see here that it's in the form of 1 over n to the p power. So this diverges by the p-series test, and that's because the p is equal to 1. All right, for the alternating series test, it is decreasing. All right, 1 over 1, 1 over 2, 1 over 3, 1 over 4, excluding this guy over here, ignoring that. If it's 1 over n, it's constantly getting smaller and smaller. The limit as n approaches infinity of that 1 over n would be equal to 0. So this converges by the alternate series test. All right, so it says find the interval, center, and radius of convergence. All right, so the interval of convergence is going to be going from, well, the negative 2 is part of the interval. So negative 2 less than or equal to x. The positive 2 is not part of the interval. The center of convergence now that's actually pretty simple now that we know what the interval of convergence is. It's the center of this interval of convergence, so that would be 0. You can write x equals 0 if you want. Radius of convergence (2 units). At most 2 units, really, because on one end it's equal to negative 2, and the other end it's not equal to a positive 2.